Hello everyone. In this work, I will introduce the modeling of spiking neural networks inspired by global feedback connections in the brain. The training of spiking neural network has always been one of the difficult problems for researchers. In addition to the backpropagation algorithm, the researchers want to learn from the brain to update the weights of the neural network. It is well known that the brain uses the law of synaptic plasticity to regulate the strength of connections between neurons, and most of the current methods for modeling synaptic plasticity, such as spiking timing-dependent plasticity, long-term plasticity, and short-term plasticity, are all unsupervised local optimization rules. That's to say, when we apply these local optimization rules to the network, we do not provide a supervision signal to the network, which makes it difficult for the network to converge when training a deep spiking neural networks. Anatomical and physiological evidence shows that there are a large number of feedback connections in the brain in addition to feedback-forward connections. Learning and reasoning in the brain are based on the interaction of feed-forward and feedback connections. Numerous feedback connections connected feed-forward connections in reverse order, passing global information from higher cortical areas to primary cortical areas during learning. Feedback connections from higher layers compute predictions of low-level representations. The weights are updated by combining the differences between the states of the feed-forward and feedback neurons and a local synaptic plasticity mechanism. First, our network computes the state of the network using feed-forward connections. Then, we calculate the difference between the predicted value and the true value, and directly calculate the target of the predominant layer. Finally, we use the feedback connections to calculate the target of the different hidden layers of the network. And finally, uses the local synaptic plasticity rule to calculate the weight changes between different hidden layers. The feedback layer is directly connected from the output layer to the hidden layer. That is, the entire network can update the parameters of all hidden layers at the same time. And since the feedback layer does not need to update the weights, no additional computation is introduced. We implemented our algorithm using the basic components in BrainCog, which we will describe in detail later. In order to prove that our algorithm still performs well after the number of network layers is deepened, we test the accuracy under different hidden layers, and the number of neurons is set to 256. As shown in the figure, for the method of equivalent propagation, when the number of network layers is deepened, the accuracy drops from 90% to 9%, and it becomes difficult to converge. This is because the equivalent propagation algorithm is similar to contrastive hyperlearning. Two stages are defined in the learning process. The minimized energy function is used to perform implicit feed-forward and feedback propagation. When the number of network layers is deep, the network is very difficult to converge to a stable state. Compared with other stable algorithms, the performance of our proposed algorithm is improved whether it is in 3 hidden layers or in 6 hidden layers, which shows the stability and superiority of our algorithm. In order to study the effect of the feedback connection on network performance, we created the 7, 8, 10, and 12-layer networks respectively. All hidden layer neurons are set to 200. First, we remove all feedback connections from the network, which means that only the weights of the last two layers can be updated. Then we gradually add feedback layers to the network to see how the network performs. As the number of feedback layers increases, the performance of the network gradually improves. When all feedback layers are added, our algorithm achieves optimal performance. It fully shows that the feedback connection plays a very important role in the process of learning. And in the BrainCog framework, we implement the corresponding algorithm. We used the basic component leaf neuron in the BrainCog framework. As shown in the code, our algorithm is divided into two stages, the forward and the feedback. In the forward stage, the leaf neurons are used for forward propagation, and the fine rates of neurons is used as the state of forward propagation. The different targets of the hidden layers are updated with feedback connections, finally combined with the states of the feed-forward and feedback connections. The local synaptic plasticity law is used to update the weights. We also provide a detailed training script. And if you are interested in our work, welcome to set our article. And if you have any questions, please contact us by email. And thank you.